Since we're talking about forces, Isaac Newton will be the scientist that we will be studying most in this chapter. You might remember Isaac Newton from the story where the apple fell from the tree, landed on his head, and he said, "Aha, gravity." Well, that might not be exactly how it happened, but he did observe an apple falling from a tree, and using the work of Galileo and the scientific method, furthered that observation by coming up with a hypothesis. He did tests on his hypothesis, experiments on his hypothesis, and later turned it into a theory. So he did figure out gravity from this observation. And what gravity is it affects all motion throughout the universe. It's that 9.8 meters per second squared value that we talked about in chapter 4. It's just Isaac Newton actually put a name to it and did the studies on gravity, and realizing that gravity is an acceleration of sorts. It's what's pulling objects towards the center of Earth. He's most famous for his works, the Principia, which is a book that formally defined concepts and equations. So he discovered calculus, and then also, of course, the law of gravity, which is a lot of what this chapter is going to focus on. We're also going to talk about other forces and his 3 laws of motion. So what are Newton's 3 laws of motion? First one is an object at rest tends to stay at rest, and an object in motion tends to stay in motion unless acted upon by an outside force. The second is going to define our first equation of this chapter, and that is force is equal to mass times acceleration. So when we're calculating force, we're going to need mass and we're going to need acceleration. And the last law of motion is for every action, there's an equal and opposite reaction. So what we're going to do is we're going to look at each of these laws a little more closely and some examples of each. So Newton's first law. This one is also known as the law of inertia. And what inertia is the tendency of an object to resist any changes in motion. Okay, so this is the reason that the tablecloth trick can work. Because inertia basically is saying that an object doesn't want to move. Right? An object at rest wants to stay at rest. An object in motion wants to stay in motion. So for the tablecloth trick, what we have is dishes, silverware on a tablecloth. And what are those dishes and silverware doing? Nothing, right? They're motionless. They're not moving. So they have a certain amount of inertia, a tendency to resist any change. So since they're motionless, they don't want to move. So if you can pull that tablecloth fast enough, they won't move because their inertia, their resistance to change, is going to keep them where they are there on the table. Okay, and we're going to see a lot more examples of inertia as we go through chapter 5 and chapter 6. So Newton's first law is the law of inertia, where objects resist any change in motion. So now let's look at some examples of the first law of motion. So we have an object at rest. So you can see the picture of the soccer ball here sitting on the grass, at rest, not moving, right? It's going to stay there. It's not going to move unless acted upon by an outside force. So in the next picture, the outside force is a person kicking the ball. They're applying a force to the ball, making the ball move. Now that that ball is in motion, it's going to want to stay in motion. It's not going to want to stop. Okay, because it's going to resist any change. It has a certain amount of inertia. So an object in motion will continue in motion unless acted upon by another force. Okay, so that force could be the ball going into a net, because that net, therefore, is now stopping the ball. Sometimes, though, you don't need a net. Sometimes the ball just keeps rolling and eventually stops, right? But there actually is a force acting upon it, making it stop, and that's the force of friction. So usually it stops because the ball is on grass, and the grass over a certain distance applies enough force to stop it. That's why oftentimes if you're kicking a ball around, you don't necessarily want to do it on cement because it's going to keep going till it hits grass or something else that has a lot of friction. to apply that force to change its motion. Some other examples of Newton's first law would be a car running into a wall, right? So you have a car in motion and it's not going to stop. It doesn't want to stop. It's going to resist any change in motion until it runs into a wall, that wall being an outside force being applied to the car. Now hopefully that doesn't happen, and instead the outside force that you're applying is the brakes. Playing pool is another example. All of the balls on the pool table are motionless until someone hits them with the cue, causing an unbalanced force moving the otherwise still ball. Air hockey is another example, and then bowling as well. So the examples are all around us, really. Okay, now let's look at Newton's second law. So what Newton's second law is this defining force through an equation. So force is equal to mass times acceleration. Okay, this accounts for the change in velocity when a force actually does act upon an object. So for this equation, we are going to be using it, applying it in some word problems and doing the calculations. When you solve for force, know that the units are newtons, capital N, for Sir Isaac Newton, who did all the work on these 3 laws of motion. Okay, right next to the newtons here, that kilograms times meters per second squared, that's what newtons are made up of. The kilogram coming from the mass portion, because we always need mass in kilograms when we use them in physics problems, and then the meters per second squared portion coming from the acceleration side of the equation, because acceleration is measured in meters per second squared. All right. Next, we're going to look at net external force. Now, this isn't something we're necessarily going to be calculating, but I want to show you all of the forces that are actually acting upon us on a daily basis. Okay, so looking at this picture, we have 2 people pushing a wagon with a person in the wagon. Okay, so we have an acceleration, this A value with this yellow arrow. That means that that wagon is accelerating to the right in this picture. So what forces do we have? Okay, well, we have F1 from one of the people pushing the wagon. That's the force they are applying to the wagon to get the wagon to accelerate. And we also have F2. Notice all these forces are being represented by arrows, and arrows are vectors. So yes, force is a vector quantity, having a direction and a magnitude. So we have 2 forces from the 2 people pushing the wagon. Okay, now we also have a force now going in the other direction, this little f down here. And what that is the force of friction. Okay, so we talked about that a little bit with the soccer ball, right? If a soccer ball is rolling on the grass is applying a force in the other direction, stopping the ball. Okay, so there's a force of friction. Now, those forces are kind of easy to see. You know, you can tell if someone's pushing something, they're obviously applying a force to it. But the ones that are a little harder to see is this W pointing down towards the ground. Okay, and what that is a weight force. So that wagon and the person in the wagon, they weigh something, right? They have a mass, they have a weight. So they are actually applying a downward force on the earth. Now, think about this. The heavier that person is, the harder it's going to be to push the wagon. Why? Because of that downward force that they're applying on the earth. Now, for every action, there's an equal and opposite reaction, and we'll see that in Newton's third law. So we have the weight force pointing down into the ground. We're also going to have a support force, this N value here, that is being applied back up toward the wheels of that wagon. Okay, without that force, without that support force, the wagon wouldn't be able to stay on the ground. It would fall through. So net forces are additive. So you can add F1 plus F2, but you need to be aware of all the forces and count them all when you are doing additions. So all the external net forces added together would equal the net force. So it's a combination. Remembering that force is a vector quantity, and that the units are newtons. Looking a little closer at Newton's second law. So what we're going to do now is, we said force is equal to mass times acceleration. Now we're going to look at proportionality. So an object accelerates proportionally to the net external force and inversely proportional to its mass. Okay, so what does that mean? Proportional means if one goes up, the other goes up. So since acceleration and force are proportional, if the force goes up, acceleration goes up. So if there's more force, there's more acceleration. So that's what proportional means. One goes up, the other does too. At the same time, if one goes down, the other's going to go down. So they're going in the same direction. Okay, so in these examples here, the more force applied, the more the acceleration, right? The harder you push that lawnmower, the faster the lawnmower is going to go, the faster it's going to accelerate. The harder you push that car, the faster it's going to go. So one goes up, the other goes up. Now let's look at how acceleration and mass. Now, they are inversely proportional. So force and acceleration were proportional, meaning if one goes up, the other goes up, right? But acceleration and mass now are inversely proportional. So that means if one goes up, the other goes down. All right, so the examples I have here, notice the force vectors, these arrows are approximately the same size. So we're applying the same force to both these wagons. If there is a small mass, so the mass is low, that means the acceleration is going to be high because they're inversely proportional. Mass is low, mass goes down, acceleration goes up, opposite directions, inversely proportional. So in the next example, applying the same force, but with a larger mass. So now the mass went up. And since mass and acceleration are inversely proportional, if the mass goes up, the acceleration is going to go in the opposite direction, down. That wagon's going to be moving slower. Let's look at Newton's third law. So the last law of motion. And this law is for every action, there's an equal and opposite reaction. So much like this Newton's cradle, this is actually what this is called. You might have seen them on desktops. If you pull one of the balls and you let it go and it hits, and the other one goes back and it just keeps going back and forth. Okay, so this is for every action, there's equal and opposite. That's what causes this thing to continue going and going and going. So when an object exerts a force on a second object, the second object has to exert an equal and opposite force on the first. So let's explain this with some examples. If you throw a ball on the ground, right, it's going to bounce back up. The harder you throw it, the higher it's going to bounce, because whatever force you apply on that ball, it's going to exert an equal force in the opposite direction. So if I throw it down hard, it's going to come up high. If I throw it down soft, so low force, it's going to not bounce very high. It's going to bounce low. Another example here, if you're standing on the edge of a boat, right, you want to jump off into the cool water. Okay, so this person is jumping forward. So when they jump forward, what's actually happening is they're applying a force on this boat. Okay, they're applying a force, they're pushing off of the boat, causing the boat to go in the opposite direction. All right, so they're jumping one direction, the boat's going to go the other direction, especially if it's a canoe or some, not a boat with a heavy mass. A few more examples. Letting the air out of a balloon, right? If you let the air out of the balloon, the air is going to go one way and the balloon is going to go the other. Action, reaction. Equal and opposite. Shooting a rifle is another example. If you've ever shot a rifle before, it's got a kickback on it because the bullet is going out with great force in one direction, and so you're going to feel that with an equal and opposite force on your shoulder in the opposite direction. Punching someone in the face. This is a great example of action-reaction pairs. If you punch somebody in the face, you are exerting force on their face, but you're also going to feel that force, equal and opposite, back on your hand. So the harder you punch them, the more your hand's going to hurt, right? Equal and opposite. Shooting a rocket into the air. Hot gas goes down towards the earth, shooting the rocket up in the sky. Equal and opposite. The more fuel, the more force, the higher that rocket's going to go. Now some examples that aren't quite so dramatic. The force of your finger on a wall. So even right now, you could push your finger on the wall. The harder you push your finger, the more force you're applying to that wall, the more you're going to feel it back on your finger. You can even get to the point where it hurts if you apply enough force. And one that you might not see every day is that weight force. So for instance, just a book sitting on a table. That book is applying a force on that table. And that table is actually applying a force, equal and opposite, back up on that book, allowing that book to stay present on the table. If it wasn't applying a force back on the book wouldn't be able to stay suspended on the table. So now let's look at another kind of force. So we've only looked at one type of force so far, and that's been linear force, where we had mass times acceleration. Okay, so before we do any calculations, let's look at weight. So F of W is what we're going to represent by the weight force. So weight is a force. Like we think of weight as, oh, the scale says 150 pounds, lb, right? Well, that's not a force. In physics, weight is a force. It is our mass, how much material we are made up of, multiplied by gravity, because gravity is what's pulling us towards Earth. That's what's causing objects, masses, to have weight. So it does depend on gravity, so we are going to be using that 9.8 meters per second squared. Weight changes based off of your location. If you're on Earth, gravity is 9.8 meters per second squared on Earth. But if you went to the moon, gravity changes on the moon, so your weight is going to change depending on where you are. Mass, however, will always remain the same. So if you are talking about a 10 kilogram boulder, okay, that's a mass, kilograms, and you bring that boulder to the moon, it's still made up of 10 kilograms. It didn't lose any mass. It's still the same size, but its weight's going to be different because now it's in a different gravitational pull. It's went from the Earth, higher gravity, to the moon, lower gravity. I want you to keep in mind when you are doing weight calculations that force is still going to be measured in newtons, so that's not changing at all. Okay, so it's very similar actually to our free fall equations when we were doing zero initial velocity equations in chapter 4, and we could replace all of our A's, all of our accelerations, with G's when it was free fall, because free fall, the only thing affecting that object falling was gravity. So it's very similar here. We just took the force equation and replaced the A with a G. So these next few problems that you're going to see on the next slides, there is a video of me working these problems out on the whiteboard so you can see the step-by-steps. There is also a practice worksheet, which is the homework that I handed out before this break, with an answer key as well. So I recommend you look at the video, try some of those problems, the practice problems on your own, and then look at the answer key, see if you got them correct before you try taking any of the homework quizzes.